Hello students, today's lecture is on orbital velocity of the satellite. When we launch a satellite into the orbit, what is its orbital velocity? So that it is orbit stable, so that it remains at a suitable distance from the Earth and continues to revolve around the Earth, right? So what we do is that we launch a satellite from the Earth by some rocket booster, and it goes and goes, but the gravitation of the Earth will try to pull it down, and the gravitation force will change its velocity both in magnitude and direction. When it goes up and up and up, we have launched the velocity v. It is a launching velocity, not the orbital velocity. And finally, when it reaches this position, then here its velocity becomes perpendicular to the gravitational force. The moment its velocity becomes perpendicular to the gravitational force, from there onwards, the direction of the velocity changes, but not the speed. Speed remains constant, because force is perpendicular to the velocity now. And then the satellite will maintain the orbit because force is perpendicular to velocity. Now this force will provide the centripetal force, and the satellite will continue to move in an orbit of radius, suppose r. So the concept here is that launching velocity is more than the orbital velocity, because you have launched it with higher velocity. But finally velocity decreases, but direction also changes, and finally when the velocity becomes perpendicular to the force, the angle is 90, and from there onwards the direction of velocity changes, but not the speed. Therefore this force will provide the centripetal force to keep the satellite in its orbit. That is all. So here we have learned this launching velocity is more than the orbital velocity. Launching velocity is greater than the orbital velocity. So what is the equation that we want to write? Find the orbital velocity. If the radius of the orbit is r and radius of the Earth is r, capital R, mass of the Earth is m, and mass of the satellite is small m. So what should I write? F is equal to ma, the same Newton's formula for constant mass. So what is F? Force, that is gravitational force here. That gravitational force is G, capital M, small m by r square. That is gravitational force. It is m, mass of the satellite. And what is V? What is the what is the acceleration of the satellite moving around the Earth in an orbit of r? That is, as you know, that is the centripetal acceleration, and that is given by speed square by r. That is centripetal acceleration. 1 r gets cancelled, this gets cancelled, and we get v0 is equal to orbital velocity root of yahan ja karke g capital M by r. That is the answer for the orbital velocity. So if the orbit of the satellite, if the radius of the orbit is larger, then the orbital velocity will decrease. If the radius of the orbit will increase, the orbital velocity will decrease. This is the base formula for the orbital velocity of the satellite. The important thing here is that the orbital velocity of the satellite does not depend upon the mass of the satellite, because mass of the satellite does not exist in the final equation. So orbital velocity of the satellite is independent of the mass of the satellite, not of the Earth. No, of the satellite. Here capital M is the mass of the Earth, right? So there's a point which is worth noting, worth to be noted, that is the orbital velocity does not depend on the mass of the satellite. Right? So it's very easily done. The orbital velocity is root of gm by r. As we go away from the center of the Earth and put the satellite deeper and deeper into the space, quite away and away, then obviously the orbital velocity will decrease, because this r is the denominator. Right? Okay. Next point is The next point is, if the satellite is made to revolve in an orbit, if the satellite is made to revolve in an orbit which is somehow hypothetically made inside the earth, अगर अर्थ के अंदर एक टनल बनाया जाए, circular tunnel around the center of the earth, hypothetically, and a satellite is made to revolve in that tunnel, in that circular tunnel, what will be its orbital velocity? It's a very important thing. Of course, this is quite hypothetical because you can't make a tunnel inside the earth, or there is no such thing as to move a satellite inside the earth. There's no such thing. But let us hypothetically think about it and see if there we can make a tunnel inside the earth, in a circular tunnel inside the earth, around the center of the earth, and try to move a satellite in that orbit. What should be this orbital velocity? So let us see. Okay, we have the formula, that is V is equal to root of gm by r. This is r now, from the center of the earth. But this is the formula when the satellite was revolving outside the earth. Outside the earth. And this m was the mass of the earth. Same formula we have. But now this mass is not the mass of the whole earth, it is mass of this part around which the satellite moves. Because of the inverse square law, this mass will not create any force. This mass, which is outside this tunnel, which is outside the circular path, that is insignificant. That is unimportant for this satellite moving in a circle. This mass will not act. That's because of the inverse square law of gravitation force. So what should we write here? M prime. M prime is the mass inside. That is all. Of course, we can later get the equation in terms of capital mass, but base formula is this. The satellite will move inside the earth in a circle due to the force on this satellite will be created by this M prime, mass enclosed by the circular orbit of the satellite. That is very important. If you ask me why, I will give the answer that it is a remarkable example of inverse square law. Because gravitation force is inverse square 1 by r square, and because of that, this will not act. This part of the mass will not act. Anyway, okay. Now V0 is equal to root of g by r. What is M prime? That is 4 by 3 pi small r cube rho, density of the earth. It is volume of this, and multiply rho, this density of that. So V0 is equal to this r, this will be r square here, and r will come out root of 4 pi g by 3 and rho. Here we have an important concept now here. That simply means the orbital velocity is proportional to r for constant density of the earth. If we suppose the density of the earth is constant, it is proportional to r. That means if the satellite is very closer to the center, its orbital velocity will be less, because of r less. If r is increased, then the orbital radius will increase, the speed of the satellite will increase and increase and increase and increase and increase. And when it is on the surface of the earth, orbit is very closer to the surface of the earth, just outside, then the speed will be maximum. And from here onwards, speeds will decrease as we have the formula gm by small r square, because then it will be outside and the speed will decrease if you go out. But within the earth, if you go from center onto the surface, making the orbits inside, the speed of the satellite will go on increasing just onto the surface. And from surface onwards, the speed of the satellite will go on decreasing. This follows almost the same rule as the acceleration due to gravity. Acceleration due to gravity is 0 at the center, and it goes on increasing just onto the surface. And from surface onwards, the acceleration due to gravity decreases. That is what we know. But here it follows almost the same rule. Okay, now here the orbital speed is proportional to r. If we plot a graph, let me plot a graph between orbital velocity and r. So it will be something like this. It is r, it is center of the earth, and it is orbital velocity. So here at the center, if it is just at the center orbit, that will be the orbital velocity will be 0 because r is 0 there. It increases right up to the surface. Here it is r. Can you tell me what is the orbital velocity at on the surface of the earth? That is orbital velocity is equal to root of g capital M by r. Small r is replaced by capital R of the outside formula. And then it decreases as 1 by root r. As we have the formula outside, V0 is equal to root of g m by small r. This is the rule. At the center, the orbital velocity will be 0, and then the orbital velocity will go on increasing if you make the orbits around the center of the earth, and finally the orbital velocity will be maximum. और अगर इसका वैल्यू भी चाहिए आपको इस ऑर्बिटल वेलोसिटी सरफेस ऑफ द अर्थ का, सो इट इज, अगर मैं सबस्टिट्यूट करूंगा सारा कुछ ये भी और ये भी, तो मुझे मिलेगा 7.9 किलोमीटर पर सेकेंड. अच्छा खासा वेलोसिटी है ये. इट विल बी फास्टेस्ट ऑन द सरफेस ऑफ द अर्थ. इफ द सैटेलाइट इज जस्ट closer to the surface of the earth revolving, it is the fastest velocity, 7.9 kilometers per second. You can well imagine. So one more example I want to give you. One more example that I want to give you is point third. We have we know it that there is in the space there's gravitational dust, gaseous material. There's quite gaseous material in the outer space. Something like this, gravitational dust. The gravitational dust particles are a little apart, but this is a dense gas type system in the universe itself. And there are two stars revolving in circles in this gravitational dust of mass, maybe m1 and m2, but orbital velocity never depends upon mass. So it is r1 and it is orbit is r2. The question is, whose velocity will be more? Whose orbital velocity will be more? It is V02, it is, okay, a V01. They are revolving in the space and revolve not around some particles, some stars or some sun-like structures. They are revolving in the dust. This dust here, this dust acts as a mass, the way sun acts as a mass. This dust acts as a mass. So whose velocity will be more? The velocity of the second m2, v2, will be more than v01. The answer is because this mass revolves around a small mass. It encloses smaller mass. It is the same example as I have given you, the examples inside the earth. This revolves around some mass which is less, and this satellite revolves some mass which is more. And according to the rule जो अभी हमने किया है, orbital velocity is r root of 4 pi g rho by 3. Just now I have this formula. So जितना ये दूर हो जाएगा सेंटर से, सेंटर ऑफ दिस इंटरस्टेलर डस्ट से, इंटरस्टेलर जो डस्ट है इससे जितना भी दूर हो जाएगा कोई भी प्लेनेट हो या स्टार हो, उसका वेलोसिटी ज्यादा होगा, बिकॉज दैट एनक्लोज मोर मास. तो दैट विल फॉलो दिस फॉर्मूला, जितना दूर r, बिकॉज अगर इस डस्ट का डेंसिटी हम कांस्टेंट माने. It has been proved by the scientists that the stars which are far away from the center of that cloud, they have more velocity, orbital velocity. So this is very important. The velocity, this will be more than this, because this satellite, when it moves in a circle, it encloses more mass, which is responsible for its orbital velocity. This was the third example. And finally, I ask the students to watch my lectures regularly on the YouTube. I am available there. Thank you for watching all my lectures and encouraging me to continue my lecture series on the YouTube. Thank you.